Greenland looks, from space, like a white shield floating at the top of the world. But that white shield is not just snow. It is one of Earth's largest frozen systems, the Greenland ice sheet, a mass of ice so large that it covers about 80% of Greenland's surface. It stretches almost 2,900 kilometers from north to south, reaches more than 1,100 kilometers across at its widest point, and holds enough frozen water to influence coastlines around the planet. This is not a mountain glacier or a seasonal blanket of winter snow. It is a continental-scale body of ice, built up over vast periods of time, layer by layer, under its own crushing weight. Understanding Greenland's ice sheet means understanding one of the clearest signals of a warming planet. The scale is difficult to picture because the numbers are almost unreal. On average, the Greenland ice sheet is about 1,673 meters thick, which is more than a mile of ice in many places. At its deepest, it reaches over 3,488 meters, thicker than many mountain ranges are tall. It covers roughly 1.71 million square kilometers, an area larger than many countries combined. Only Antarctica contains more ice. Scientists often shorten the name to GIS or GRI, but the simple abbreviation can hide the sheer physical force of what it represents. Ice at this scale behaves almost like a slow-moving rock. It spreads outward under gravity, flows toward the coast, and feeds glaciers that eventually meet the sea. The Greenland ice sheet did not appear overnight. Greenland has held major glaciers and ice caps for at least 18 million years, but a single ice sheet first covered most of the island around 2.6 million years ago. Since then, it has grown and shrunk as Earth moved through colder and warmer climate periods. Ice sheets are archives as well as landscapes. Their layers trap clues about ancient air, dust, snowfall, and temperature. The oldest known ice in Greenland is about 1 million years old. That means the ice sheet is not just a frozen mass, it is a climate memory bank. When scientists drill into it, they are reading a record of past atmospheres and past worlds. In a stable climate, the ice sheet works like a giant balance sheet. Snow falls in winter and adds mass. In summer, some surface ice melts, and outlet glaciers release icebergs into the ocean. For thousands of years, gains and losses could roughly balance over long periods. The system was never perfectly still, but it could remain broadly stable. The problem now is that the balance has changed. Due to human-caused greenhouse gas emissions, Greenland is currently warmer than it has been for the past 1,000 years. The ice sheet is losing ice at the fastest rate in at least 12,000 years. That matters because when an ice sheet loses more mass than snowfall replaces, the missing ice becomes water entering the ocean. Surface melting is one of the most visible signs of change. In summer, parts of Greenland's surface darken, meltwater streams appear, and blue pools form on top of the ice. These melt ponds can absorb more sunlight than bright snow, which can accelerate local melting. Some meltwater drains through cracks and shafts, reaching deeper layers or even the bed beneath the ice. This water can affect how ice moves, although the details are complex. The key point is that melting no longer behaves like a small seasonal adjustment. The ice sheet is now melting 2 to 5 times faster than it did before 1850. Since 1996, snowfall has not kept up with the losses. Another major loss happens at the edges, where glaciers flow into the sea. Ice cliffs break apart through a process called calving, producing icebergs that drift away into the ocean. Calving is natural, but warming air and ocean conditions can make it more intense. When outlet glaciers speed up, thin, or retreat, they can drain ice from the interior more quickly. This is one reason Greenland matters globally. The ice sheet is not isolated from the ocean. Its coastal margins are active gateways between land ice and sea level. A change in those gateways can affect how fast ice stored far inland begins moving toward the water. Sea level rise is the reason Greenland's future is not just a Greenland story. Since 1972, Greenland's melting has already contributed about 1.4 centimeters to global sea level rise. That may sound small, but global sea level is measured in averages spread across the entire ocean. Even a few centimeters can worsen coastal flooding, storm surge, erosion, and saltwater intrusion into freshwater supplies. Between 1901 and 2018, sea level rise from all sources was about 15 to 25 centimeters. Greenland is only one contributor, alongside thermal expansion of warming seawater, mountain glaciers, and Antarctica. But Greenland is one of the largest potential sources because of the enormous volume of ice stored above sea level. The future depends heavily on emissions. Even if the Paris Agreement goal of keeping warming below 2 degrees Celsius is achieved, Greenland ice alone is expected to add around 6 centimeters to global sea level rise by the end of this century. If emissions are not reduced, the contribution could be around 13 centimeters by 2100, with worst-case estimates near 33 centimeters. These numbers are not predictions of total sea level rise, they are only Greenland's share. The difference between 6 centimeters and 33 centimeters is not abstract. It represents choices about energy, infrastructure, land use, and climate policy. The ice sheet responds to physics, but the pathway is shaped by human decisions. The most dramatic number is the total potential. If the entire Greenland ice sheet melted, global sea levels would rise by about 7.4 meters, or roughly 24 feet. That would redraw coastlines, threaten major cities, and transform low-lying regions around the world. This would not happen by 2100, and it would not happen all at once. Ice sheets respond over centuries and millennia. But long timescales do not make the issue harmless. Some climate thresholds can commit the planet to changes that unfold long after the original warming. In other words, a decision made during one century can lock in consequences that continue for many generations. Scientists are especially concerned about temperature thresholds. Research suggests that global warming somewhere between about 1.7 degrees Celsius and 2.3 degrees Celsius could make the eventual loss of most of the Greenland ice sheet likely, even if the complete melt takes thousands of years. At 1.5 degrees Celsius, Greenland would still lose ice equivalent to about 1.4 meters of sea level rise over the long term. If temperatures rise above that level and only later decline, even more ice can be lost. This is why climate timing matters. It is not only the final temperature that counts, but how high warming gets, how long it stays there, and how quickly the world reduces heat-trapping emissions. Beneath the ice, Greenland is not flat. Hidden under the frozen surface are mountains, valleys, and lake basins. This buried landscape affects how the ice moves and how vulnerable different regions may be. Ice resting on sloping ground can behave differently from ice sitting in a basin. The shape of the bedrock influences drainage, friction, and the pathways that glaciers follow toward the coast. Because so much of this terrain is covered by kilometers of ice, scientists rely on radar, satellites, aircraft surveys, and models to map it. The Greenland ice sheet is therefore both visible and hidden, obvious as a wide expanse, but full of unseen structures that shape its future. The Greenland ice sheet is often described through numbers: kilometers of length, meters of thickness, centimeters of sea level rise, degrees of warming. But behind those numbers is a simple story. A vast frozen system, built over millions of years, is now losing mass faster than it can recover. Some change is already unavoidable, but the scale of future change is still not fixed. Lower emissions mean slower loss, less sea level rise, and more time for coastal communities to adapt. Higher emissions mean faster melting and a greater risk of crossing thresholds that are difficult to reverse. Greenland is not just melting ice. It is a warning system, written in white, at the top of the world. If you found this helpful, please like this video and subscribe for more explainers.